Good morning, everyone. Today, inshallah, we will continue our lectures regarding optimization. Today, we will finish the pre-optimization and hopefully we will go through the unconstrained optimization. Our table is really very tight for the time being, so all I need from you is to start studying as much as possible and as fast as possible, as our midterm is just round the corner, and I will need you to focus and study and go through what we did previously in the previous lectures, especially the part 4, how to identify the quadratic equations or the quadratic part in an equation, an optimization problem, the how to identify if your matrix is positive definite, positive semi-definite, and this part is really very important. We will need it down there. I will start this optimization lecture by once more raising that the main basic concepts and tools in optimization, we need to focus on the concavity and convexity and how to study them perfectly. Also, there will be a details of the arguments and the images which is connected with every function that you are aiming to find its optimal point and the value of the maximum. As I told you, it's really very important part in our course, as life is all about optimization in everything. Everything you do, and we did go through this in the previous lecture, whatever you intend to do is related to optimization. You optimize your efforts, you optimize your workouts in the gym, you optimize the use of your time, you optimize the time of studying, you optimize your expenditures, and so on. So life really is all about optimization. Let's start with the summary of the concavity and convexity, the part that we ended studying in the previous lecture. First of all, we are between the strictly convex functions or the convex functions, the strictly concave functions or the concave functions, or the functions which are not concave or convex. Okay? For strictly convex functions, those are for every a and b, and for lambda that belongs to the open interval between 0 and 1, we will find that the weighted average of the points, 1 minus lambda a plus lambda b, the image of this value will be less than the weighted images for these functions. So that's a condition to have a strictly convex function, as you can see, and we studied this in the previous lectures in details. Also, to have a convex, it will be the same relation, but you may have some points where these two values, the image of the weighted average equal the weighted averages, and this may happen in the convex functions. For the concave functions, for strictly concave functions, the inequality will be the opposite. So the image of the weighted average of these points will be greater than the weighted average of these images. And if they are equal to each other, then you will deal with concave case for this function. This classification is really very important in order to identify the type of function that you are dealing with and to determine the extremum points and the extremum down the road, as we will see in this lecture and on the coming lectures, of course. In the case of having none of these conditions applied, you will have non-convex or concave functions, and that's the last case. Also, before going faster, before going in the coming slides, I want you to remember that for any concave shape, convex shape like this, the line segment connecting any 2 points will be above the graph. Here it will be above or equal to the graph. In this case, they will be lower the graph, because the case of concavity, it's something like this. It's not something like a bowl and it's looking down. So once you imagine that any 2 points inside this bowl, it will be less than all the points of the function representing this bowl, as we will also see this definition in details in the coming slides, and it's written for you also. Please, before going further, I would like to say that you should visit the Moodle website. You have the main slides over there, and also you have some short videos representing also another tool within your hand to study this. Also, I would deeply recommend that you visit the old exams that already exist on Moodle, as we are, as I told you, for the midterm is really around the corner, so I need you to go over there and walk through the problems that you can find over there also. Okay, now in this part we will try to summarize some basic direct properties regarding convexity and concavity of functions. And this part will shed a light on the main properties of addition, of multiplication by scalar for concave or convex functions. If you make a composition between two main functions which are concave or convex, what's going to be the result of this, and so on. I will start with the linear functions and convexity. What we mean about linear functions: if a function is linear, its graph is a straight line if you are talking in 2 dimensions, or it's going to be represented by a line in the 3 dimension or a plane in the 3 dimension. This is very, very important. In 3D, with no curvature, so the line segment which connects points in the graph is at the level of the graph. What we mean here, if you have something like this, which is an equation of a plane, 2x minus 3y equal 1, sorry, a straight line equation, you will find this straight line connecting 2 points. If we are in 3D, then you will find all the points within the plane. There is no curvature, and we classify this case as a convex and concave case. So any function which is concave and convex at the same time, any function at the same time is convex and concave, it's called a linear function. And the 2 conditions exist for this function, which are less than or equal the value of the images of the weighted average between any 2 points. It's less than or equal, or greater than or equal in the case of concave function, so it's going to be the same. These are the 2 laws that I'm telling you, that they are shared, the equality, and once they are equal, you are talking about a linear case. Okay, a shorthand simplification or symbolization, I'm sorry, for this phenomena or for this property is f is linear, which leads to f is convex or concave function at the same time. Of course, the proof is really very simple. All you have to do is to use the lambda equation, which with the image of the weighted average of these 2 points, and comparing them for both cases, and you will find them equal to each other. That's the deep explanation for all of this. I already sent you the detailed proof, but I don't want to take time going through the details of the multiplication of this. It's just only straightforward proof. Okay, the sum or difference of convex and concave functions. For the sum of 2 convex or concave functions, strictly or not, result is a function with the same classification. That means if you have 2 functions strictly convex and you added them on each other, the result will be strictly convex function. If you have a convex function for both of them and you added them together, so the result also will be a convex function. And same goes for strictly concave and for concave functions. So this symbol stands for strictly concave functions, and that symbol for concave functions. This symbol stands for strictly convex functions, and same way like this symbol symbolize the case of convex functions. So once you add two functions from the same type, the result would also be the same type. The explanation is very, very direct, very simple, and also the proof is direct, straightforward. So if you imagine that I have G, which as you can see a convex function, and if you have F, which is strictly also convex function, and you get the addition of these two functions both together, you will have F plus G, and if you are getting a line segment between any 2 points, either on F or on G, and added them together, the result also will be exactly the same for the F plus G, as you can see. So once more, once they have the same condition, you will end up the same case, you will end up by the addition to reach that result. Also, as I told you, the proof is really very direct, or it's just only expanding the main equation of lambda and adding them together, and you will end up having the same condition, either in the case of convexity or in the case of concavity. Okay, perfect. Now we will go to the product of concave or convex functions in a scalar value or in a value. In this case, all you will have is just either increasing, if I'm talking about a convex function in specific, if you multiply in a positive value, you will cause an increase in this convexity. And if we multiply by a negative value, this convexity will take the opposite. So if your function is convex and you multiply by a negative, it's gonna be a concave function by a negative value. If you multiply by the 0, you will come to the case which is not concave, not convex. All of this is written here in this paragraph, which states that the product of convex or concave functions, f, strictly or not, by a positive, negative, or null number, results in a function with respectively the same. If you multiply in a positive, you writing in convexity, it will be convex, the opposite. If you multiply in a negative, and it's gonna be a linear function in the case of a 0, or you will erase this property. So this is once more a strictly convex function for convex function, for strictly concave functions, for concave functions. If you multiply by a certain number to half or whatever, which stands for positive, an example for positive values, so the result will be also strictly, it will be strictly convex, it's going to be convex, and the same goes for the other two types. But if you multiply in a value that's less than 0, which is a negative number, so if you have a strictly convex function, it's going to be a strictly concave function. If you have a convex function, it's going to be convex function, in a negative, it's going to be a concave. So what we mean is the type of this classification will take the opposite shape. This will appear from here. If you wrote to f, we have a concave function. If you multiply by 2, all what's going to happen is increasing the concavity degree, as you can see. So here's f, and here's, once we multiply by a 2, the concavity will increase. If we multiply by a negative value, instead of having a concave function, in a negative value, it's going to be a convex function, as you can see. And also, if we multiply by another positive value, okay, in this case, so the concavity will increase. If we multiply by null, we will have the null shape, which is a concave and convex at the same time. So finally, we can summarize the multiplication by scalar by, if we multiply by a positive number, the curvature increases, okay, or decreases but remain the same. Because if you multiply in 2, the concavity will increase. If you multiply by half, the convexity will decrease. The concavity will decrease. Okay, if we multiply by a negative number, the curvature will be the opposite convex, will be concave and vice versa, for example. If we multiply by 0, we will have the null plan, which is concave and convex at the same time, as we spoke about this previously. Now we're coming to a very serious point, which is the composition of two functions. One of them is convex or concave, and the other one, through this composition, is also concave or convex. This is a very nice property for these functions once they are composite to each other. So the composition of two functions with the same classification regarding convexity, one of them being strictly increasing, results in a function with the same classification regarding convexity. Okay, let's go through the details of this application. So let's say that I have an f which is strictly convex or concave, blah blah blah, and we have h which is concave, convex, and in both two cases, and convex in the other. Convex in the first two cases and concave in the other two cases. So h is strictly increasing, strictly increasing. These are the cases, and the results will be, if you have the composition h of f, then you will have strictly increasing, strictly convex, and the convex strictly concave and concave function. I believe the coming slide will give a good demonstration about these properties in details. So once more, let's review the main definitions that we are dealing with. Once more, remember that convex function, a function is convex if its graph looks like a ball facing up. That's the convex function. So it's like a ball and it's facing up, edges 8 facing up. And it means the line between any 2 points with this ball, it will be lie above the graph of this ball. So that's a definition for convexity once more. In the case of concave function, so it's gonna be like this, a ball looking down. So any point, any line segment connecting any 2 points, it will be below the surface of this curve. And here the definition in details, I've tried to write it for you and give you this description just to make it easy for you to remember. It's a graph looks like a hill or a ball facing down the line between any 2 points lies below or beneath the graph. Monotonic function is either increasing. What we mean about increasing function, as x increases or as the input increases, the output also increases. This is what we mean about increasing function. So as the input increases, the output also increases. What we mean about decreasing functions, while the input increases, the output overall decreases. Okay? So once more, as the input increases, the output will go down. And for f and g of x, their composition, it means the following. That's f of a g of x, which means we insert x inside of g, and the result will be inserted inside of an f. So this means plug x into g, then plug this function into f. That's the meaning of the composition. That's a very nice definition for everything that we will deal with. Convexity and monotonicity, both together. Okay, whether f of g of x is convex or concave, it will depend on 2 things. So either this function is concave or convex, it will depend on 2 main properties, as you will see. Whether f is convex or concave, so the f function, the outer function, is either convex or concave, and also the outer function is increasing or decreasing. So I have 2 conditions related to the outer function or the outer frame or the the main function, which is f, okay? First of all, I have to identify if f is convex or concave. Then I need also to be sure about its status regarding increasing or decreasing. So f is convex or concave, f is whether increasing or decreasing. Then I will go through g, which is to identify if it was a concave function or a convex function. Then we will do the composition. Let's say if f is convex and increasing, g is convex, though their composition will result in a convex function. So once more, the first function or the outer frame or the outer function, if it was convex and increasing, and the inner function is also convex, so the result will be a convex function. I've simplified these cases in the following table, which summarizes this property explicitly. So, first of all, if f is convex and increasing, these two conditions related to the outer function, and if she is convex, so the result will be convex. The second line is very important. If you have f is convex and decreasing, convex and decreasing, even g is concave, so the result will be convex. So actually, the thrust or the tension in the outer function will govern the result of this composition. Also, if f is concave and increasing, and the inner function is concave, you will have no issues, it will be concave. But if you have the outer function concave function, and it is in the decreasing direction, and the inner function is convex, the result will be also concave function. So these are the results and the cases, the various cases regarding the concavity and the monotonicity. The result might not be convex or concave functions if one of these conditions were broken. So if the outer function convex or concave, you will have to answer this question. Is it increasing or decreasing? This should be outlined. And also the inner function convex or concave, because the three factors affect on the choice of the function as I told you. Example, one of the nice examples that I thought to add it to these slides is the example of, let's consider the exponential function, which is f of x equal e of x, which is really very simple. If you remember, that's the y-axis, and that's the x-axis. This is positive infinity, and that's negative infinity. Same, negative infinity, and that's a positive infinity. And that's the graph of y equal to e to the power of x, which represent a function that's convex function. So e of x of itself, it's a convex function. That's a first condition is checked. And also it's an increasing function, strictly increasing function. As x go higher or as x increases, you will find that the y also increases. So it's a increasing function, strictly increasing function. If I'm talking about an inner function, which is a g of x, this is y, that's positive infinity, and that's of course x positive infinity and negative infinity. If we are talking about x squared, that's a y equal to x squared, which is the convex function. Adding these two guys together or putting them together will result in, for sure, a convex function. So it's very simple, as I told you. That's a convex and increasing function. That's also a convex function. So the composition between both of them, which is simply, if I got f, okay, f composite g of x, you will end up having e to the power of x squared, which is, as I told you, a convex function. So it's really very simple.